So, hi everyone, and good afternoon. Our speaker today is Dr. Pawel Przytarski. He's a Marie Curie Fellow working between University of Melbourne and University of Genova. And he's going to talk about unsteadiness in turbomachinery flows, multi-scale interactions, and their quantification. So thank you so much, Pawel, for accepting our invitation. We're looking forward to hearing your talk.
Yeah, thank you for the introduction. Yeah, well done for making it to the call. I think the time zone may have confused quite a few people. It definitely confused me this morning. I definitely woke up and tried to join the wrong time meeting. But anyway, without further ado, let's go to the next slide. Is that gonna work? Yeah. So here is an outline of today's talk. I'm gonna talk a little bit about unsteadiness in thermomachinery flows in general, and then we're gonna go into large-scale flow decomposition, multi-scale kinetic energy, transport equation formulation, quantification of those energy transfer rates. And then if we have enough time, we can go into two extra topics, one of them being the impact of the state space. And then we'll finish it up with a bit of a summary and future work. So starting with the unsteadiness in thermomachinery flows. I guess just to start, what turbomachinery flows are. Turbomachinery flows can be found across a wide range of applications, including compressors, turbines, fans, pumps, and propellers. Basically, whenever there is an interaction of a fluid with a rotating component, that can be classified as turbomachinery. Here is an example of a cross-section of a jet engine, which consists of quite a few turbomachinery components. At the front, there's a fan, followed by a compressor, and then finishing at the turbine. So looking into the jet engine, into a compressor section of it, since I mostly focus on the compressors, you'll see that it's made up of multiple stationary rotating parts. If you take a cross-section of them, they look like airfoils. Current design practice for those rotating machinery tends to rely on geometrical models combined with reduced set of physics and empirical correlations. These methods are well validated for existing systems, but the problem is that if we're trying to design outside of past experience, these methods are not validated for them anymore and they struggle, which means that design innovation requires accurate modeling beyond the current design envelope. So why is that a problem? Well, low fidelity methods model unsteadiness and a lot of physics related to it, which tends to lead to uncertainties that exceed desired efficiency gains. So if we put a probe in a compressor flow field, you'll find out a turbulent spectrum, which consists of those peaks. This peaks corresponds to rotors or the blades passing, and a harmonics, broad inertial range, and a dissipation spectrum at the end. Schematically, people tend to represent this as this graph on the right, where we have deterministic, where the turbulence or unsteadiness is split into deterministic component and stochastic component, where the current practice tends to use low fidelity methods such as runs, U-runs. Actually, runs and U-runs are kind of on the expensive end of things. Typically, we would use even lower fidelity methods, such as 0D, 1D, and 2D methods. And then on top of the limitations of the low fidelity methods, some of the methods require certain assumptions. For example, U-run requires so-called spectral gap between deterministic and stochastic unsteadiness, which is that gap represented between the large and the small scale, which is in practice hardly ever present, and the design trends tend to be such this gap becomes smaller and smaller or non-existent as the machines become more compact and work on higher work coefficients or require more work to be done. So if we look at what such a flow field may look like, here is an idealized compressor made up of stationary rotating parts. What's interesting about it is that axial compressor offer interesting test case for studying unsteady interactions. So it's both interesting from the kind of fundamental perspective and from the practical perspective, since those flows are a backbone of power generation and aerospace aero engines. So they're worthwhile studying. Even starting from clean inflow, we can see that there's a lot of unsteadiness that gets generated across the flow path, and that unsteadiness arises due to the propagation and accumulation of wakes and due to turbulence generation in upstream passages. So the turbulence that we see here, obviously there is some component of at the very end. I don't know if you can actually, maybe I can start here, laser pointer. The turbulence or the unsteadiness that you see at the end, it has some coherent or discrete component due to rotor wakes, but a lot of turbulence in between comes purely from the accumulation from previous stages. What's also interesting is that after several blade draws, turbulence reaches a sort of equilibrium as overall passage turbulence production balances the dissipation. So if we take, for example, this blade draw and this blade draw, and you compare them on a statistical basis, you'll see that they're very similar to each other. So at some point, those turbulence quantities and their impact on the flow field sort of saturate and become repeatable to an extent. Another thing to mention is that the unsteadiness that we see here depends on both compressor design and its operation. So an example of that, we can look at one of the design choices of the multi-stage compressor. If we take a baseline design and we decrease the gap sizes between subsequent blade draws, you'll see that this has an impact on the unsteadiness that those two flow fields show, and then that translates to, for example, higher deformation of wakes, higher unsteadiness levels, etc. So this can be summarized into this kind of flow of thoughts. More compact compressors lead to stronger interactions between the blades, and that tends to increase in flow unsteadiness. And it's important to consider that because turbomachinery blading has to be designed to operate in those highly unsteady environments. And at the moment, that is hugely simplified. Another aspect of it is the unsteadiness depends on the operation. So even though we may design compressors for the cruise conditions of a plane, which is where the gas turbine operates most of the time, it also needs to be able to handle conditions at the takeoff, during the ascent, and during the landing descent. And that translates to different places on the so-called compressor characteristic, descent requiring less work than ascent. And that also translates to very different flow fields, which we can also blend into. So this would be the on-design conditions, the conditions that the compressor would be designed for, which minimizes the loss. And then on the left-hand side, we have this takeoff condition that is highly unsteady, and you can see a huge difference in the flow field, specifically due to the thickening of the suction side boundary layer, which then translates into more unsteady flow field downstream, and that has a kind of feedback effect on the blade. And on the opposite end, during a descent, the pressure side, so the bottom boundary layer thickens, and that also increases unsteadiness to a certain extent, but not as much as on the first case. And then we can statistically characterize those flow fields. For example, we can compare them to some experimental data from different research compressors. These are the C106, CIT, LSRC. So these are the Cambridge University compressors. And these studies were done in the past. The blue dots correspond to the simulations that I showed you, last one. And this point corresponds to our descent condition. So when the plane is landing, and this condition corresponds to our ascent, where the plane is taking off. You can see that the kind of trend follows roughly what the experimental compressors show. The differences are due to design, the simplifications of the setup, and so on and so forth. And then we can also look into those flow fields and extract the free stream spectra. By the way, although if it wasn't clear, all the data that I'm showing is computational. These are scalar resolving simulations. They're of the well-resolved, highly well-resolved LES/DNS resolution. And these spectra come from those computational simplified setups of multi-stage compressors. And you can see how the spectrum kind of changes between those two cases. I'm not going to go too deep into it, but this is just to show you that unsteadiness plays a big role, and it's dependent on both the operation and the design of a compressor. So that's a little bit of a background of why it's worthwhile to study the unsteadiness and why it's both important. It's both interesting from the fundamental perspective and from the kind of industrial application of it. Now going to large-scale flow decomposition. So high-fidelity simulations, like I showed you before, are very expensive. These sort of simulations would go into millions of CPU hours or tens of thousands of GPU hours. So it's important to extract knowledge and derive models from them as much as possible. Historically or typically, we would collect the flowing data sets, time average data, phase average data, maybe probes in the free stream, snapshots for visualization purposes. But the problem is that you kind of already need to have a hypothesis on what sort of physics you're fishing for before you define those data sets that you're planning to create, to collect. So standard approaches utilize only a fraction of available data and tend to rely on expert-driven analysis. So you as an expert need to decide what you're interested in before you perform such a simulation. So this kind of alternative to that is scale decomposition applications. Many people have heard of methods such as POD, proper orthogonal decomposition, DMD, dynamic mode decomposition, and such. What these methods allow us to do is split the flow into multiple components. So instead of performing a standard averaging, so the so-called Reynolds decomposition, when we split the flow field into the mean and fluctuating components, we are able to perform a sort of multi-scale decomposition where we still have a mean, or we can retain the same mean, but then we have multiple modes which build or which correspond to our flow field. And this sort of analysis tends to be used to estimate losses due to various dynamics. So we can compute mean flow dissipation due to our mean strains and the production per each scale or per each mode, which tends to look like this, where we can quantify loss or quantify turbomachinery energy, production, dissipation, whatnot, versus a mode number. So that's all nice because it helps to identify lossy dynamics compared to the classic Reynolds decomposition, but it has certain limitations. Nonetheless, it's a good first step to create a sort of multi-scale description of the flow. So to perform that, I'm gonna show a method to do it, which would be a proper orthogonal decomposition, where we collected 500 snapshots of this simulation. So it's 500 snapshots. The simulation the section of the simulation that I showed you corresponds to roughly 170 million points, and we're gonna collect 3 velocity components, UVW. That corresponds to roughly 250 billion points altogether. You can put that into a huge matrix and perform or solve an SVD problem that splits that flow field into spatial modes and temporal coefficients. To show you what those look like, here is a kind of selection of certain modes that proper orthogonal decomposition gives you. So, for example, the mode 1 is strongly related to those wakes or the wakes that upstream rotor leaves, and you see those strong signatures of those rotor wakes. Mode 40 corresponds to large-scale structures within the boundary layer, and the mode 400 to small-scale structures. So that gives you an idea that POD sort of decomposes the flow and sorts it into dynamics or scales of different size. Together with spatial modes, each spatial mode would have an associated temporal coefficient attached to it. So mode 1 has a purely sinusoidal or periodic or very repetitive repeating pattern of temporal coefficient. Mode 40 looks like this, and mode 400 looks like that. To give you a better idea of what POD did and what those modes correspond to, we can perform an FFT, or fast Fourier transform, each of those signals, and construct this this spectrograph of sorts, where each mode gives you, and this can be translated in frequency, can be put on this graph. So we can see that mode 1 was purely related to the wake dynamic, and it had a single frequency present in it. Mode 40, that corresponds to roughly this, has a more broader spectrum that doesn't correspond to any of the frequency peaks, etc. And then at the very bottom of it, you'll see kind of broadening of spectra, which corresponds to kind of dissipation scales within our flow. But this, if this reminds you of something, I'll be a little bit suggestive here, and I'll compare it to our free stream spectrum, which looks qualitatively quite similar, where we see those peaks also being represented through the model decomposition. You have a fairly broad inertial subrange, which here would be depicted as this linear band of frequencies that were found by the model decomposition. And then you have a broadening of spectra due to dissipation spectrum at the bottom. So data-driven methods such as those can identify and isolate dynamics and coherent structures within the system. So that's pretty convenient. Now, that's not all the story. So that kind of leads me into the next point, which is the multi-scale kinetic energy transport equation formulation. So while what I said is true, that those data-driven methods can decompose the flow and kind of characterize it and put it on the spectrograph like this, which gives us a nice qualitative understanding of what's happening in the flow and which mode is responsible or corresponds to what dynamic. The dynamic importance of each mode is actually unknown. That information of which modes are dynamically important for the flow physics are embedded in the so-called triadic interactions. And then these interactions show the pathway of energy from the mean flow to turbulent dissipation. So just to give you a little bit of separation, so turbulence production calculates how much energy is extracted from the mean flow. Triadic interactions show how that energy that has been taken from the mean flow or from the inflow or from anywhere else cascade down towards the dissipation scales. So triadic interactions are kind of, or have this kind of aura about them that they're difficult to understand. So I'm gonna present you an intuitive way to understand them, and that will set up a framework for what I'm gonna show you in the future. So typically when we collect the data or when we decompose the flow, we do the Reynolds decomposition, where, as I mentioned, we split things into the mean flow and the fluctuating component of the flow, the so-called turbulent field. So our total kinetic energy can be split into kinetic energy and turbulent kinetic energy. These two have their corresponding transport equations. As you can see, those transport equations are almost identical. The only difference is the sort of operation that we're performing on them, where advection, or the transport of kinetic energy or turbulent kinetic energy, is equal to production, dissipation, and diffusion. Now, these terms are separate or different. They're similar, but kind of separate because of the different operator that's working on them, except for production, which is shared. That production is a very important term because it couples two transport equations. And then for reference, those components, the convection, production, dissipation, diffusion are written out here. The alternative to that, if you want to take a step forward, would be a Hussein-Reynolds decomposition. This would split the flow field into the mean, oscillating component, and then this turbulent component or fluctuating component. Now the total kinetic energy can be split into mean kinetic energy, periodic kinetic energy, and turbulent kinetic energy. This leads to 3 transport equations. They're almost identical to the equations before, except now we don't have a single production that couples the system, but each transport equation or each scale has its own production associated with it, which means that we have a sum of productions on the mean. And then there is an extra term that couples the 2 scales, the periodic and the turbulent scale. You can see that this term is exactly the same, but it has a different sign. So here it acts as a source, and here it acts as a sink, or well, the opposite way. But anyway, what's also interesting is that this transport term, or later we'll find out this is a triadic term, has a very similar formula as a production term, which means that it acts on Reynolds stresses and uses a strain of a periodic field instead of a mean field as before. So that kind of gives us intuition. So if that's what happens if we have 3 scales, if we have multiple scales, then something similar must be happening. And just to show you that those formulas, the operators are identical, I'm going to flip between the 2, and you'll see that all the formulas have exactly the same kind of structure. The only difference is the kind of operator that we do, the sort of averaging, the difference between mean averaging and kind of phase averaging. But if we want to go to multiple scales, I kind of gave you an idea of what happens as you extend your decomposition into multiple scales. Instead of having 3 scales, so the mean fluctuating, mean periodic and fluctuating, you have mean and as many components or as many scales as you want. So now total kinetic energy can be split into mean and turbulent kinetic energy. As before, the transport equation for the mean kinetic energy is exactly the same as with a triple decomposition. And the scale kinetic energy is effectively just an extension of turbulent kinetic energy and periodic kinetic energy. You can see that they both have a convection per scale, production for each scale. There is a triadic component, or the transfer of energy, which is can be both a sink and a source. You have a plus and a minus. There's a dissipation, and then there's the diffusion. So it's not such a big extension of what we've done in the Reynolds decomposition or triple decomposition to go from those 2 decompositions into a multi-scale decomposition. And that's the sort of framework that we're going to keep in mind when we're going to discuss triadic interactions. So knowing that this is the case, let's try to quantify those energy transfer rates or triadic interactions. If we look at the structure of these triadic terms, they look like this. This is similar to the production that I showed you before, where we have some sort of Reynolds stress and strain, except now those fluctuating or those velocity components can relate to 3 different scales, L, M, and N. That means that if we have many scales, we can potentially, we have potentially interactions between all of them to the power of 3. So for example, we have 100 scales. Each one of those 100 scales can interact with any 100 scales and another 100 scales to create a triadic. That's why it's called triadic, because you have 3 different scales interacting with one another to that manage the flow of energy. So for our case, because we have 170 million points, and those triadic interaction can happen at every point of the domain, we have 170 points. We have 500 snapshots, which means we have potentially 500 scales, and they can interact each in any combination. So we have potentially 170 million times 500 to the power of 3 potential triadic interactions, which translates to a very large number of 2 times 10 to the power of 16. So it's difficult to compute them. There's a lot of them, but that's exactly what we tend to do. We evaluate all those interactions using high-performance computing, loading all the data, decomposing it, and computing all those interactions. And when you do that, you obtain this sort of cube where you have 3 different scales, a scale N, a scale M, and a scale L. And you can see how those 500 cube interactions all behave and all happen. This is the net transfer rate or net triadic interaction. So it has been summed up over the 170 million points of the domain. And you can see that, interestingly, actually most of the interactions result in no flow of energy. Most of the interactions happen along those 3 diagonals. Now, that's still very difficult to interpret of what that means. So what we can do is we can sum up through all the triads for each pair, because ultimately what we want to understand is how does energy flow from a single scale to another scale. We want to kind of fix the sink scale to the source scale. And that allows us to sum it to this sort of turbulence cascade. So it's a data-derived energy cascade. And what it shows us for the scale with the multi-stage compressor is that there's this vertical lines corresponds to scales or modes associated with wake and its harmonics. And the dark red color means that those scales, those wake-related scales, act as a source of energy for all the scales down the turbulence cascade. So they energize across the entire spectrum of turbulence, and they allow for the energy to flow from the big scale or from the large wake scale into all the scales in inertial range and dissipation range. You also see that there is a little bit of a blue color towards the top. That means that there are certain scales which signify backscattering events. That means that the energy flows from a smaller scale to a larger scale. So in the opposite direction to the energy spectrum. But that's a pretty interesting picture because it allows us to qualitatively explain or visualize what's the flow of the energy across our very complex turbulent flow field. Now, what's more about it is that now, once that we have everything split up into those scales, we can also perform budgets on those flows. So for each scale, we can quantify what is the production for each scale within a flow. We can also quantify what is the dissipation, how much each scale contributes to the dissipation. We can show what the net triadic effect or net triadic transfer each scale has. What it means is that the scales below the zero line on the net act as source of energy and transfer energy down the cascade. And on the positive end of the spectrum, that means that those scales on the net or on average receive energy from the larger scales. We can also quantify advection, and then the work to obtain all the diffusion terms is still ongoing, but we can see what the difference or what the residual for each one of those scales is. And that, that still requires the future work, but that shows you that we're very close to balancing the budget, not just for the entire flow field or not just in the boundary layer. We're balancing the budget of scale kinetic energy for each scale across the entire spectrum. And we can understand what role each one of those scales plays in this behavior that is governed by those scales. For example, the very interesting point on the triadic transfer rate, so the blue line, is the crossover point, where these scales are mostly generating energy and sending it down the spectrum, and these are only receiving energy of the spectrum. One of the key assumptions behind large eddy simulation is that you're trying to resolve all the scales which are kind of important in governing the dynamics within the flow field. This tells us exactly where does the line of those significant dynamics is, at what frequency does it cross, and at what frequency the scales become mostly dissipative and can be probably modeled in a very effective way. Now, I don't know if we have enough time, because I'm not sure how long the presentation is supposed to be, but I can talk about the impact of the state space, but I'm gonna skip through those slides and jump into the summary and future work. And if we have time during the Q&A, I can revisit those topics. So I'm just gonna jump through the sort of thing, and then we can come back if anyone wants to discuss it in a bit more detail. Now, finally, that we were able to both decompose the flow and quantify all the triadic interactions within it, we can discuss the future work. So this sort of decomposition and evaluation is very powerful because it allows us to transform this complex simulation and represent it in the form of a dynamic system. It's a very popular idea that has been pursued by multiple authors. But what it basically means is that now that we have decomposed the flow into spatial modes and into triadic interactions, we can effectively transform our flow into a problem of where the kind of the derivative of the flow is the sum of the linear component and nonlinear component, where linear component corresponds to those spatial modes and nonlinear is effectively embedded. The information about nonlinear component is embedded in the interscale transfer rates. Many people study that. So for example, DMD method is trying to estimate that linear relationship. And then that kind of stems from the Koopman analysis and so on, while the resolvent analysis is trying to understand the impact of forcing on the amplitude of the flow and how the two are related. So the fact that we're now able to decompose the flow and evaluate both of those terms means that we are now able to construct low-order models and assess control strategies. For example, switching off and on certain dynamics to see what the impact on the amplitude is of the kind of resulting field. Another direction that one can take this sort of work is you can classify scales depending on their spectral signatures and obtain like a reduced turbulence energy cascade. So for example, we can take all those scales related to blade passing frequency and its harmonics. We can take the sub scales, so scales which are like on the lower frequency that our blade passing frequency, and our dissipative fine scales, and then leave the rest as the large scales. And we can construct the reduced data-derived energy cascade and construct a sort of phenomenological description of the energy cascade. This is a very simple split, but you can imagine, for example, hand-picking modes which are related to Kelvin-Helmholtz instability, and trying to understand how those Kelvin-Helmholtz modes relate or how they transfer energy down the energy cascade to understand, for example, which frequencies are most important for that transfer of energy, and also for control strategies, if there are certain frequencies that you want to, or certain dynamics that you want to avoid more than the others. So that gives you this sort of array, and the sort of visualization of it allows you to see how are dynamically different dynamics connected to one another. So just to summarize what I've been talking about for this presentation, we're trying to kind of answer this big question is, can we use unsteady high-fidelity data to discover hidden turbulent dynamics? And to do that, we used a high-fidelity multi-stage compressor simulation, as shown here. We extracted 500 snapshots, full 3D snapshots with 170 million points each. We performed a large-scale decomposition. The one that I showed you was roughly of an order of 5 terabytes. That allows us to split this data set into the spectrogram and the resulting modes and temporal coefficients. Then we can compute all the triadic interactions that are that play a role in the simulation, and it's purely data derived and doesn't cut any corners. We don't make any assumptions of which interactions are important or not. We just evaluate them all, and then that allows us to construct this data-derived discrete energy cascade that carries the information about energy, net transfer of energy between any two modes or dynamics. And then finally, that allows us to perform some system reduction and dynamic system modeling on the data set. So all this work that I showed you allows us to now characterize unsteadiness within a compressor flow field, and we're working towards formulating a reduced order model of unsteady interactions to replace empirical correlations using industrial design tools. All of it is for the purpose of kind of cutting off all the assumption-heavy augmentations and empirical correlations and replace them with something more physical. So that's it. Thank you for showing up. Here are some acknowledgements for the work for the people who helped me produce some of this work that you saw in this this presentation. And if you have any questions, feel free to ask them. Thank you.
Oh, thank you so much. That was a very interesting talk. If anyone has questions, feel free to either speak up or type in the chat.
Yeah, hi, Pawel. Good, really good presentation. Some amazing graphics and results. I did wonder, with this kind of level of detail in your flow analysis, have you got the same level of detail in an experimental comparison to check this? Because it's incredible level of detail, and I know for a fact that measuring experimental data from compressor cascades is extremely challenging. So if you want to comment on that.
Yeah, that's very difficult. The closest method to what I showed you, the kind of DNS equivalent of experiments, would be PIV, and then efforts are made to do PIV measurements, but then they become very difficult close to the wall because of the reflections, because of the experimental setup difficulties. So that is indeed difficult. And then there comes another question of spatial resolution, that PIV can't quite give you the same level of detail as DNS. Having said that, I do have a active collaboration with the University of Geneva, where another MSCA fellow is working on that, and we're in the process of creating or generating a kind of matching heterogeneous data sets of the flat plates with contoured end walls between DNS and PIV at matching conditions, so that we can kind of explore a little bit more of how such a merging or assimilation of experimental and computational data can happen. With PIV, you can still perform all the analysis that I described here. However, certain detail will be missing. So I think ideally what you want to do is either combine the two data sets or inform what is missing from the PIV data. So what is missing very close to the wall. I guess there's still a couple of open questions of how you would go about it, but I'm definitely exploring this sort of things as well.
And does Cambridge, because I know Cambridge has UTC with Rolls-Royce, I think it's a compressor UTC. Have they attempted to supply data like this, or what's their position on this?
Yeah, I've collaborated during my PhD with Andy Wheeler, who's of Little Laboratory in the University of Cambridge. They do have certain data sets. However, the problem is that with those experimental rigs, many of them are Rolls-Royce labeled or Rolls-Royce related, so that data is often proprietary or would require a certain financial resource to buy the kind of experimental running time on those rigs, which is difficult as I don't currently manage big budgets like that. So maybe for the future, but not right now. There's another question about the PAV. While they did PAV in the past, I'm not aware of the current active PAV setup in Cambridge. That may happen in the future, but I don't think they have one now.
Right. Okay. So there is actually a gap out there somewhere to generate some of this data in some form, from the sounds of it.
Potentially. I guess it all depends on the sort of application and the end goal or the objective of it. But yes.
Yeah. Okay, thank you.
Also a question in the chat from Kushal, who's asking, can you comment on the selection of time scales to do the simulations? Is it the Kolmogorov time scale?
I guess the simple answer is the time step has been determined by the CFL condition for running the simulations, the compressible simulations. For the collection of the data, I didn't consider time step per se. We've collected, or I've collected roughly, I think that translates to 100 snapshots per rotor period, something like that. I'm pretty sure that's higher than Kolmogorov timescale. Yeah, so I guess that hasn't been one of my concerns. Potentially worth exploring. We did do a little bit of a sensitivity on the POD and sort of discrete energy cascades that we can generate based on the number of snapshots and the frequency of saving. But honestly, we haven't seen much sensitivity to it. So I know that for some of the simulations, the spatial resolution has to be of an order of 10 Kolmogorov length scales. I'm pretty sure on time scales, you can probably go even higher than that. So I guess that the kind of bottom line is you want at least 10 Kolmogorov time scales, but probably more, way more. As in, like, you don't need to be so strict or have data at such high frequency. You can go much lower frequency.
Thank you. Do we have any other questions?
Yeah, I've got one more question. So these techniques, Pawel, can they be applied to other turbulent flow systems? Is it generic enough, or is it very specific to these kind of compressor interactions and wake interactions?
No, they're applicable to any method, just as runs is applicable to any method or any setup that you can obtain large number of high fidelity snapshots would work with that. There's nothing inherent in it. There's nothing inherent in it that kind of limits it to apply to any sort of problem, as long as there is some sort of dynamic relationship between the scales at play or modes at play. If you're trying to decompose the problem, you could technically apply it to magnetohydrodynamics, and that would work perfectly fine. Or any other multi-phase flows where there's a dynamic relationship between different scales. Nothing specific about this that makes it, that limits it to the compressors. It's just the compressor is a kind of nice setup because it's both industrially relevant, and then it kind of decouples the problem from inflow conditions. You can start from a purely laminar inflow condition, and you're assumption free in terms of generating realistic flow fields that you can then study in detail further down your compressor.
Great. Okay. Thank you. That's all for me.
I guess we thank you there for the very great talk. We really enjoyed it. Thank you everyone for joining, and we hope to see you at the next webinar.
Thanks very much.